the last half of section 1.3, start off looking at special cases, difference of squares. I mean, an easy one would just be factor x squared minus 9. How does that factor? Yeah, everybody got that right. Feel good about that. But what if it was a plus y to the 4th minus 16? Is that still a difference of two perfect squares? Sure. How do we factor that? Leave it alone. A plus y. Oh, what's the square root of the 4th power squared? Plus what? Oh, well, no. If I said z to the 4th minus 16, yeah, I'm going to go z squared plus 4, z squared minus 4, right? So z squared plus 4 and z squared minus 4. Am I finished? Still have another difference of two squares, right? So you can use brackets or parentheses. I don't care. And then you're gonna have a plus y, what, plus 2 times a plus y minus 2. See how that works? Just keep that blob all together and don't be thrown off by it. Don't be thrown off that this is an a plus y. It's just a thing to the 4th power, right? So it is a perfect square. Just like when we got down here, the thing squared minus a perfect square. Another difference of two squares, right? So feel good about that? Good. Anybody remember how to do the difference of two cubes? You said we talked about that. There is a soap thing, same. Yeah. Well, I'll teach you the way I learned it in 10th grade and never forgot it. And don't laugh. But you take the cubed root and you put them down. You see what I did? Cubed root of x cubed is x. The cubed root of negative 8 is negative 2, right? So say that with me. You take the cubed root and you put them down. All right, come on. Even my engineering kids did this with me this morning. They did. At least 2/3 of them did. Who's going to do it with me? Ready? You take the cubed root and you put them down. That's the part everybody remembers. But then you square the first. See, once you put the cubed roots down, you ignore the starting one. Okay. Square the first, change the sign, multiply them together, and square the last. That's the way you do it if you want to do it fast. Actually, some kids changed it. That's the way you do it if you want to pass this class, but not really. But so so say it with me. You take the cubed roots and you put them down. Square the first. Say it. Square the first. Change the sign. Multiply them together and square the last. That's the way you do it if you want to do it fast. I never forgot how to do the summer difference of cubes, okay? So Miss McCarty. I think she came up with it. I learned it from another teacher, but do you want to write it down? Square the first. So you take the cubed roots and you put them down. Cha-cha-cha. Cha-cha-cha. Just kidding. Square the first. What do you do next? Change the sign. Multiply them together. And square the last. That's the way you do it if you want to do it fast. All right, what are we going to do for this one? Take the cube roots and put them down. Cube root of 1,000 is 10, right? What do? Square the first, change the sign, multiply them together, and square the last. That's the way you do it if you want to do it fast. Will, are you bored, silly? You already knew how to do it. Did you remember how to do it from before?
I can't write stuff down.
Oh, okay. And if you want, some kids like took pictures of it at the end. If you want to do that, that's fine too. So, just recognizing some other special ones, like if I had 16x squared minus 24x plus 9. This one's not really the difference of two squares. This is just another special case. But if you recognize the first one as a perfect square, is it? It's like 4x quantity squared. The last one is 3 squared, right? Multiply 4 times 3, what do you get? If you double it, this is a perfect square trinomial, isn't it? Like Pascal's triangle thing. This is 4x minus 3. Quantity squared, isn't it? Remember? Now, could we have still just done the same stuff, you know, multiply and split them up? You could do it that way too. But if you recognize this, because that'd be a lot of big numbers, right, to deal with. So, I'm still just going to call this special cases because these are ones that you've done before. When you see 4 terms, what do you usually think? Factor by grouping. When you got 4 terms, yeah. And I usually just group the first 2 and the last 2, right? What can factor out of those first 2? X to the 4th. And what's left? Plus 1. Here, there's nothing really to factor out. You could call it 1, but you don't have to. You do have to address that the 1 is left, right? X plus 1 is common. X to the 4th plus 1 is left. All this ringing a bell? Feeling comfortable with it? So let's go back to those weird ones. I don't even think we can call this special cases. I think we need to just think of, I don't know, just start looking. We've got fractional exponents. I don't want you to be afraid of them. I do just want you to remember, if I'm factoring out, we have x's in all of them, right? So if I'm factoring out a GCF, a greatest common factor, ignoring the fractions and stuff, just tell me what you usually think of when you're factoring out a GCF. What power do you pull out in front? We did the factoring out of GCF last time, right? Let's go up here. If I had x to the 6 plus 2x cubed plus x squared, what we take out an x to what power? Squared. What power is that? The lowest power, exactly. Keep that same thought. Factor out the lowest power. Same thing if we have fractions or positives or negatives. What is the lowest power between? Everybody agree with that? Lowest power. Same process. Factor it out. Now what are we left with? Kevin, for the first one. Factored out x to the negative 1/2. We're just the plain old 3, right? For the next one, factoring, this is what causes people the most headache. I know there's going to be some x's left, right? So I'll tell you the way I think of it. You know, some people always think, oh, I just subtract. I subtract whatever I took out. I think of, what would I add to the negative 1/2? Because when we multiply like bases, we add, right? What would I add to the negative 1/2 to end up with a positive 1/2? 1 whole, right? Good job. Plus. Same thought process. What would I add to a negative 1/2 to end up with a positive 3/2? How many halves? 4 halves, right? And 4 halves is actually 2. So now, once we got rid of the ugly negative exponent, I'm going to go ahead and switch it around, because for some reason I have a master's degree in math, and I just hate trying to factor with them written this way. So I always take the time, rearrange them. XX plus and plus. What are the numbers? 1 and 3. The only things that multiply to give us 3, right? And 1 plus 3 happens to be 4. So it works. So, started out looking scary, right? Is it really that scary? Not really. So let's combine. Everybody get that one down? 6. Let's combine the blobs with the fractional exponents. Don't be upset that it's not a plain X or whatever. This is a matching blob, right? So how many of those could be the GCF of those two terms? What power? the 3/2, the lower of the two, right? And I think you jumped the gun, because once you factor out the 3/2, you're going to have 4/2 left, which will be minus, factor that whole thing out, you got to keep the place with the 1, right? Now, obviously, you could FOIL that out and combine like terms, but does anybody recognize this? Difference of two perfect squares. Keep factoring. X minus 1 plus 1 and x minus 1 minus 1. But minus 1 plus 1 goes to 0, right? And minus 1 would be minus 2. Feel good? Everybody picking up what I'm putting down? All right. I didn't show the other group this one this morning. What if I have something that can be the difference of 2 cubes and the difference of 2 squares? Which one do you do first? I would have thought that as well. But if you do the 2 cubes first, what's left, that big, square the first, change the sign, multiply together, square the last, becomes really, really bad to try to factor. So always do, the easier version is the squares, right? So always do the easier one first. How does that factor as the difference of squares? X cubed plus y cubed and x cubed minus y cubed, right? And now we have 2 cubed root songs, right? So, chant it with me. You take the cube roots and you put them down. I don't hear the chuzz. Square the first, change the sign, multiply them together, and square the last. That's the way you do it if you want to do it fast. Got another one. So what do? Somebody else lead us. And you put them down. Y'all are so weak. Square the first, change the sign, multiply them together, and square the last. That's the way you do it if you want to do it fast. Woo! And what happened, if we had done the difference of cubes first, we would have had like x squared minus y squared, square the first, change the sign, multiply them together, and square the last. But notice, this gives you x plus y, x minus y, right? How in the world would we be able to split that one up into these 2 things? I do not have the skills to do that. No. So that's why it's important. If you got difference, or that would have to be difference. Difference of 2 cubes and 2 squares. Do the squares first. No, what if the directions said factor completely? if we had done the difference of two cubes, we easily can get, you know, the cubed roots, square the first, change the sign, multiply them together, square the last. The problem comes from if I know this keeps factoring, I don't know how to make it turn into these two things multiplied together. See, because I got x plus y times x minus y. I got that part easy. What I didn't get are those two things. I don't have the skills to split that up into these things. I don't know how to make it.
No, I was just thinking like take the x to the 4, x squared, minus plus, and the xy would have to be xy, and the ending would have to be y squared. Or does that not work out?
Well, what I'm saying is this trinomial has to split up into this thing times this thing. And I don't know how to do that. I mean, unless you're saying you just automatically know that it turns into that. I don't know that that's some kind of rule. I guess it could be. But I don't. It would be another big, ugly rule to remember. Let's just, I feel like how about if we do something like this? 18 y cubed x squared minus 2xy to the fourth. Factor completely. What do you notice you see first? 2 and 18. What'll come out? 2 for sure. How about the x's and the y's? 1x and 3 of the y's. So what's left? 9x minus y. And it was looking like it could have been a difference of squares, but that x and y kind of ruin it, right? So, stop. Anybody need a little stand-up break for a second? In calculus, what happens is we end up with some blobs for, you know, I don't know what else to call them. And so you can do the calculus right and yet not even know if you got the right answer because the back of the book has done all this factoring to get it there, okay? So we need to practice that understanding, you know, we need to be able to simplify at the end. How many terms do you see here?
2.
2 big terms, that's exactly right. So what factors out that's common in those 2 terms? Y to the third and nice. And then when we factor out a y cubed, what's left here? Just a y. And we factored out all the y plus 2 cubed, right? Plus, here, factored out the y cubed, so 1 there. And we need a y plus 2 to the first, right? And then the only thing would be 2y plus 2. Oh, if we're completely factoring, what else do we need to take out now? Y plus y is 2y, right? What do you see we can still factor out? A 2. pull it on out to the very front, it'd be easier. And when I factor that 2 out, what's left? Plus 1. So this is just like a little preparation to go a little bit deeper. And mainly so you can get reduced answers. So if you were faced with problem 10, what would your first thought be? Like you're thinking factoring it out. The problem is that little term right there doesn't have any right. But we can still think of this as like a big Z squared minus what? 2 times Z minus 3. Everybody agree using a little substitution? Does this actually factor? Yeah. Plus 1 and minus 3. And so instead of calling it Z, we're going to call it A squared plus 2A plus 1. A squared plus 2A minus 3. Uh-oh, are we finished factoring? If we have to completely factor this. Anybody recognize this one? 1 and 1, yeah. A plus 1 quantity squared, isn't it? What about this one? Now we're done. And let me just say, if you had taken the time to like square this thing out, distribute the 2 and combine all the like terms, it would have been an ugly big thing to try to factor down into this thing. So recognizing forms, recognizing that, oh, that's just a blob squared, minus 2 times the same blob, minus a plane 3. That's just like a quadratic that I already know how to factor, right? Now, the next type of problem is what you'll see in calculus after you've done all the calculus to it. And then you'll get this answer. You'll do all the calculus right. You'll get this answer. And then you'll look in the back of the book and you'll be like, oh my gosh, I didn't get the same thing. What did I do wrong? And you really didn't do anything wrong. And quite frankly, if you take calculus next year and you get it to this point, I will give you most of your points anyway, unless I specifically say, you know, please reduce completely or whatever. And if it's multiple choice, this will not be one of the multiple choice answers. So you'll have to go, how many terms are in this thing? It's a trick question, kind of. Hold up your fingers if you're too afraid to. This times, that's one term. Plus, times, it's two terms, right? All right. Embedded in this problem is a little issue that I have with the calculus book, because for some reason when they do their answers in the back, if there's this 1/2, they factor it out. It bothers me because it's not like it's making it any more simplified. In fact, it actually makes it slightly bigger to me. But, so let's just pretend we need to practice factoring that 1/2 out. And there's really no other numbers. There's no number that can come out of those. But how about the blobs? How many 2x minus 1s would we factor out? Good. How many x plus 3s could we factor out? This is a 1/2 power. This is a negative 1/2 power. What's the rule? Factor out the lowest, which would be negative 1/2. Exactly. So now, in term number 1, the numbers 3 times 2 are multiplied to give us 6. But I had to factor out that stinking 1/2. 1/2 times what would give me that 6? 12. Good. So see how it takes a smaller number 6 and makes it larger. It doesn't seem to be very helpful, but whatever. And so then we took care of the numbers. We factored out both of those. So there's only, a single times 1 left, right? And then we factored out an x plus 3 to the negative 1/2 power. So how many x plus 3s are left? All right. To get the 12 or the other things? Oh, okay. So you saw we factored out that whole term, so it's taken care of. Yeah, remember, we factor out the lowest power. What here, if I'm thinking distributing back, what power would I add to a negative 1/2 to get a positive 1/2? 2 halves, which is 1. Yeah. And by the way, the rule that you use to get these, it's interesting. It's always 1, because this power here is always 1 less than that power. Notice here, this power is how many less than the 3? Yeah, that's how the calculus rule is always that 1. So now we have a plus, and we factored out the 1/2, right? And we factored out the x plus 3 to the negative 1/2. So how many 2x plus minus 1s do we have? One of those, because now we know the calculus rule was only 1, right? Do some little distributing. 12 times 3, 36. So our final book answer would be 14x. 36 minus 1 is 35. Everybody agree with that? And then x plus 3 to the negative 1/2. I distributed 12 times x plus 3. 12 times 3, 12 times x.
And then where's the 14?
12x plus 2x. Just like terms in this big thingy. Now, if you were looking for your answer or the multiple choice answer and you had some fractions, how could this have been written? These two are positive exponents, right? So it could be 2x plus minus 1 times 14x plus 35. over that 2 on the bottom and that x plus 3 to the 1/2. You see how they are equivalent? So it just depends on, you just need to be able to think of different forms. That's pretty much the harshest one. I kind of hate ending on problem number 11 though. I really like doing 12. But I can't make it any longer. It's a 35-minute lesson.